now we talk about annulus, parallax, secular parallax, and now we will go to probably the most difficult topic of this lecture. That will be standard candles. 标准蜡烛法. Okay, that sounds strange. When we talk about standard candles, so this part is a little bit difficult, and if you think it's too difficult for you to understand in English, I can repeat again in Chinese. For the standard candles, what we need to focus on is the so-called variable stars, 变星，变异的就是改变的变。Variable stars, they are stars whose brightness as seen from the Earth, which means from us. The brightness fluctuates. Sometimes it's lighter, sometimes it's darker. That means variable stars. However, there are different kinds of variable stars, and for the standard candles, we further focus on the so-called Cepheid variable stars. Okay, the term Cepheid means 造父变星. Okay, in ancient China, okay, 造父，制造的造，父亲的父，造父变星. And in English or in the constellations, 在这个西方星座 it's called 鹰王座，鹰王一。Okay, 英俊的英。Okay, Cepheid variable stars is a member of okay, that's strange. Very luminous variable star, very bright. Okay, and it has periodic pulsation, which means it has regular variation in its apparent brightness. This is time, this is brightness, and it has regular changes in its brightness. As you see the spot here. It's now dimmer, darker, and later it's brighter. Is it clear here? No. It's clearer on my laptop, sorry. But anyway, this star, its brightness changes regularly. So it's called Cepheid variable stars. And it's named after Delta Cepheid, 鹰王一，是这个星座的其中一颗。The first star of this type identified, because it is first identified in this constellation. So it's called the Cepheid variable stars. This one is super important. Okay, but to give you a better impression, let's take a detour to other things. This man is Cepheus 鹰王座, okay? And here, you see a woman here. Her name is Andromeda. She is his wife. So these are a couple. And, oh sorry, that was wrong. Here, this is Cassiopeia. Cassiopeia, they are couple. Andromeda is the daughter, okay, daughter. And here we have Perseus, the handsome guy. Perseus, 柏修斯, okay? And lastly, we have Cetus. Okay, Cetus is a monster from the ocean. Okay, I wonder if that's something like a whales or, I don't know. Cetus. So we have these 5 creatures. And there's a Greek mythology like this. So, okay, that's better. Okay. Cepheus, Cassiopeia, Andromeda, Perseus, and Cetus. Okay. So the story is like this. So, and here at the shoulder is the Delta Cepheid. Okay, so this is Cepheus. So he's a king of a city called Ethiopia. Okay, and that's Cassiopeia, his wife, and Andromeda, his daughter. And however, apparently this woman, so you know in Greek mythology, the woman is always bad. So she thinks she and her daughter are the most beautiful woman in the world. So the story always starts like this. So, and this makes a person very angry. Who is that person? That person you probably know is Poseidon. Poseidon is 海神, okay? So that makes Poseidon very angry because Poseidon thinks his daughters are more beautiful. So Poseidon decided to punish these arrogant women. So he decided to send Cetus. I wonder if that is actually Godzilla. So to send Cetus to destroy the city of Ethiopia. And then there's a person like a witch said, okay, the only way to save the city, my king, is to sacrifice your daughter to the sea to Cetus. So you know the story that the daughter Andromeda is tied to the coast, and the Cetus come to collect this girl. However, here comes the Perseus and with the head of Medusa. So you know the story. So we can have fun a little bit. Okay. Variables was first identified by a female scientist. Her name is Henrietta Swan Leavitt. And she discovered that brighter, okay, now it's a little bit difficult. Brighter Cepheid variables in the Magellanic Clouds, 麦哲伦星云, appear to have longer periods. Let me read through first. She assumed that all the Cepheid variables in the Magellanic Clouds are at the same distance from Earth. So first, let me tell you, the Magellanic Clouds is not in the, it is very distant from us, very, very far away from us. So here she assumed that although in theory the distance of different Cepheid variables should have different distance from the Earth, but in general, because they are overall very distant from Earth, she assumed that they are more or less at the same distance. Okay, so that's her assumption. And then she found that brighter variables have longer periods. And now I need to give you the basic idea about luminosity and brightness. So if you buy a bulb, 灯泡, you will have two parameters. The first is luminosity, which is it's a little bit like the power of the bulb. Okay, in theory, how powerful the bulb is. However, the brightness viewed by the observer will change depending on the distance, and there is a mathematical relationship for that. Brightness is proportional to the luminosity of the light source and reversely proportional to the square of radius of this spherical space. Okay, so the more distant, then the lower the brightness the star will be. Okay, and for each star, there should be only one luminosity, but many different brightness depending on the distance of the observer. Okay, have this in mind. Let's go to this so-called periodicity luminosity relationship. So as I said, she discovered, so this is empirical, based on 经验, okay? Brighter means higher luminosity, brighter variable have longer periods, as you see from these. Okay, but apparently what Leavitt observed should be brightness. Right, because she observed from the Earth. However, she assumed that these have more or less the same distance from Earth, as I said. 因为无论如何都很远，所以距离就是可视为都一样。In that sense, the luminosity here is approximately equal to brightness, which means the factor of distance can be excluded at this point. Okay. And she observed this relationship. Then you see, there's nothing about distance here. How did she obtain distance information from this relationship? Okay. There's one thing you should keep in mind. Periodicity is easy to measure because what you need to measure is the difference in light intensity, but luminosity is difficult to measure because there's an issue of distance. Okay, so what she or the astronomer did was like this. Okay, so this is the figure you have seen is from the Magellanic Clouds. And as I said, for the Milky Way, 银河系, the distance has been determined by parallax. So we have the distance information, Milky Way, right? We know the distance. And it's very lucky that in the Milky Way, we have about 800 Cepheid type variables. 有800多个变星. And they are Cepheid type, 造父型的变星. And then for these 800 variables, you can put them into different groups. Each of them have different periodicity, different period. Okay. And then, for example, here, this group of variables, they have a period of 1 month. We put them together. And this group has a period of 1 year. We put them together. So now we will only discuss these 1 year periodicity variables. Okay? So here, for this group, for the 3 star variable or star here, they have the same periodicity. Okay? And they have the same periodicity, and their, sorry, this one. And their apparent brightness. So if they have the same periodicity, then if they look bright, which means here, apparent brightness. If the apparent brightness is high, which means this star is close to us, so the distance is low, right? And if the star looks dark, dim, then the star should be very distant from us. That's how you read this graph. And this graph is only for Cepheid type variable in the Milky Way with the same periodicity. And you can produce many these kind of plots with different periodicity. And this will be the, in chemistry we call calibration curve. Okay? So, because here we have a periodicity, let's say 1 month. These stars all have a periodicity period of 1 month. And apparently this corresponds to maybe these periods. Right? And this is in the Milky Way. And this is in the Magellanic Clouds. And in the Milky Way, we have this brightness-distance relationship. So we use this as the calibration curve to calibrate the distance of this one. I hope you get it. I saw people like doing this. Okay, Chinese. Okay, 好，现在这个是最困难的了，我再讲一次啊。这个在银河系里面有800多个变星，然后呢，这个变星有周期是10天的、30天的、100天的，就像这里写的，你就把它们分组，那分组了之后呢，你现在就只针对，比如我们说，我们现在就只针对周期都是30天的去讨论了，那这周期都是30天的话呢，我们知道，因为它是在银河系里面，刚刚已经讲过，你可以用视差 parallax 的方式把它们的距离定出来，所以这些银河系里面的这种变星呢，它都是有距离资料的，就是已知的，用独立的方法取得的，视差法取得的。然后这些变星呢，你都可以去测量它们的亮度，可观测的亮度啦，好，那当然其实你有距离，你就可以算它的光度 luminosity， 亮度、光度其实都是有的。好，然后接着呢，你就可以想象理论上，因为它们有同样的这个，因为它们都是所谓的照复型变星。那照复型变星呢，它就是有一个特点啦，就是说，在这个麦哲伦星里面，他们观察到的特点就是说，这个周期跟那个光度，它们是有正比关系的。好，然后我现在都是同一个周期嘛，那这些星呢，当它这个你观测到它的这个亮度越强的时候，就是它看起来对你而言越亮的时候，它的距离是越近，然后当它对你而言越暗的时候，它的距离是越远。好，那这个时候你就有一个，就是有点像是一个光度之于距离的一个校正公式。你可以拿光度去推出距离。好，那这个时候你是在这一个周期都是30天这一群，然后你现在是在银河系里面，你现在要去推银河系以外的星的距离的时候呢，你就可以拿这个距离光度的这个关系呢，去推 这一颗星，因为这颗星它也是有同样的周期，等于你就是外差的意思啦。啊，有人说那外差应该超级不准吧？哈，的确是超级不准，但是因为在那个宇宙，你现在讨论的距离的这个尺度可能是10的好几十次方，啊，所以你就算不准个10个1次方、2次方，可能都还算很准，啊，所以你就是用这个方式去把它大概的距离去推出来。就是用已知的去推未知的这样子，然后用的同一个锚点哦，就是说所有的星，你现在讨论的星，它们是有同样的周期，大概是这个意思哦。OK. Okay, so here it says distance is a function of brightness, and you can use it to infer the distance of this Cepheid star, a variable with this period. Okay, therefore this Cepheid is called the lighthouse or the standard candle of that galaxy. That's the reason that this method is called standard candle, because of this Cepheid. So now come back to this final Hubble's law. Distance of the galaxy and retreat velocity. Let's see if you can now better understand or have better understand this. Listen. How do you know the distance of a galaxy? How? Sorry? Distance, not velocity.
Distance.
Distance.
I forgot it.
You forgot it. I just said. 凭证.
The triangulation and the circular parallax.
And any more? Triangulation and parallax is the same method.
Oh.
Triangulation is like a 土木科学, 三角测量. In 宇宙学 it's called parallax. Okay. And anything else?
And
You don't know. Sally. Doppler effect. No. Distance. Exactly. Cepheid variable, or the method used. The method is called a standard candle, and the tool is called Cepheid variable. So to determine distance, there are basically two methods. The easy one is parallax. The more difficult one is standard candle. Okay, to determine the x-axis. And retreat velocity. Anna, how do you determine retreat velocity? How? Okay, you don't know? Yeah?
Redshift.
Redshift, right, redshift or Doppler effect. So these are the key concepts of this class. And then with this, Edwin Hubble proposed the Big Bang theory. Okay, and this is actually the case, like a Young's case, so I will skip it. Okay. So here we have velocity in the unit of centimeter per second. We have distance in the unit of centimeter. Therefore, recast this equation will give you time, right? Distance versus is actually the inverse of the slope here. Distance versus velocity. is time. And now we know the answer. The start of the universe is 13.7 billion years ago. 137亿年前. So it's quite amazing. What happened before 13.7 billion years ago? What happened? Okay, we don't know. Not, probably the time didn't exist back in 14 billion years ago. So to me, it's a very strange idea, but it seems scientifically solid. Okay, the Big Bang model. All right, and lastly, in the textbook, it's just telling you that although we know there are many stars leaving us, but we cannot tell. We can say when did the universe start, but we cannot say where is the center of the universe or where is the position of the Big Bang. This is because, assuming that you are on this train, and there's another train that leaves the station at the same time with train A. So you can hear the sound of the train, you hear the frequency change, so you know it's also leaving the train. And you are also leaving the station, leaving the station. So both trains leaves the station. But these graphs tell you it is possible that the train station is here, and train A leaves in this direction and train B in this direction. But it's also possible that it's here, and they leave in this direction, or here, or here. And you have to think it's three-dimensional. So it's possible that it's everywhere, anywhere. So you don't know the center of the universe. Okay, that's the lecture for today. So group A, you have to listen carefully. This is not in the textbook. Not in the textbook. Please search web sources. I'm sorry for that, but this is so important that I cannot skip it. Please explain Hertzsprung-Russell diagram, in short, HR diagram, okay? Please explain HR diagram. What is that? This, okay? Probably in your high school earth science, there's a picture like that. So, when explain this diagram, this is the keywords. What is surface temperature of a star? What is luminosity of a star? What is main sequence on HR diagram? How do we learn about star size from the HR diagram? And how does the life history of a sun-like star look like on the HR diagram? So a star will actually move on the HR diagram. How does it move from its beginning to the end? So this actually tells us almost everything of a star, almost. Okay, so we have to learn that. Group A. Group B. Explain. This is in the textbook. Chart of nuclides. So this is chart of nuclides. From that, we start to enter the field of chemistry. And please explain the following concepts. What is isotope and isobar on chart of nuclides? How do you read that? Isotopes and isobars. And how do you see stable isotopes and radioactive isotopes in the chart of nuclides? What is the so-called band of stability on this? What is alpha decay and beta decay on this? What is electron capture on this? And what is the relationship between N means neutron, 中子, and Z means what? Sorry. proton, and Z relationship. This is a Nobel Prize. So please study it. All right, you have more information in the textbook. See you next week.